So this is the physical science lesson video for section 18.1, and as always, if you want my videos all in one spot, then just subscribe to my channel. Alright, so we've talked about waves a little bit before, transverse waves, longitudinal waves, we went into sound waves. So now we're going to focus on electromagnetic waves. That's what chapter 18 is about. So electromagnetic waves are transverse waves, so that means they move like this, longitudinal moves like this. Transverse waves consisting of changing electric fields and changing magnetic fields, hence the word electromagnetic. An electric field is a region of space that exerts electric forces on charged particles. A magnetic field is a region of space that produces magnetic forces. So you can think of like the red portion of this wave as being the electric part and the blue portion as being the magnetic part. So if you look, there's one kind of going like this, and then there's one going like this. So it's kind of like they're together at all times. So you have an electric part and a magnetic part. Electromagnetic waves are produced when an electric charge vibrates or accelerates. This is a transverse wave because the particles are vibrating perpendicular to the direction of the wave. So remember how we talked about longitudinal is parallel and transverse is perpendicular to the movement of the waves? Because the wave may be moving this way for transverse if I'm sitting here doing like this. So the wave's moving this way, but the particle itself is going up and down. So electromagnetic waves can travel through a vacuum or empty space. So that's the difference in the mechanical waves that we already discussed. They needed a medium to pass through, like a solid or water or air or something like that. Electromagnetic waves can travel through anything or nothing, like empty space. But they can also travel through matter. The transfer of energy by electromagnetic waves traveling through matter or across space is called electromagnetic radiation. So the speed of light in a vacuum is 3.0 times 10 to the 8 meters per second. That is a constant. We'll discuss that in a second. In a vacuum, all electromagnetic waves travel at the same speed. Electromagnetic waves vary in wavelength and frequency. So since they're all traveling at the same speed, something has to be different if there's more than one type. And so that's the wavelength and the frequency. And as we've discussed before, as one goes up, the other goes down. So the longer the wavelength, the higher the wavelength, the lower the frequency. The shorter the wavelength, or the lower the wavelength, the higher the frequency. So we've already talked about this formula if you watched my previous videos. Speed of wave equals wavelength times frequency. However, since all electromagnetic waves travel at the same speed, and that is the speed of light, the speed of light is represented by c. So instead of doing v for velocity to be our speed, we do c, which is speed of light. And so speed of light is 3.0 times 10 to the 8 meters per second. So that's a constant. It's going to remain that number every time. And then of course our lambda is wavelength, which is in meters, and our nu is frequency, which is in hertz. And the important thing is, because our speed is meters per second, our wavelength has to be in meters for this type of problem. So let's look at the first one together. I already have my answer up here, but we'll still go through it together. So it says a radio station broadcasts a radio wave with a wavelength of 3 meters. So there's my wavelength, my lambda. What is the frequency of the wave? So what you'll notice is on this type of problem, they're not going to reference c or speed of light at all. And so my students, they usually have a hard time figuring out what to do because it's like, okay, well there's 3 variables, but they're only talking about 2. Where's the third one? Well, the third one is the constant. It's 3 times 10 to the 8 meters per second. So we know c equals lambda times nu. We know our lambda is 3 meters. We know our speed of light is 3 times 10 to the 8 meters per second. We're looking for nu, or frequency. So I'll show you how I got this real quick. So remember, we're solving for frequency, which is our nu. So we need lambda to be on the other side. So we do the opposite. So what's the opposite of multiplying? Dividing. So I divide both sides by my lambda. And so I get that nu equals c over lambda. And so that's how I got this formula right here. And so then once I know that, I can just plug in. So c is 3.0 times 10 to the 8 meters per second. Lambda is 3 meters. That's what they told me in the problem. If you look, your meters cancel because this is a division sign. So the 3 meters is actually on bottom. And so we're left with not seconds, it's 1 over a second, which if you remember from the previous video, that is hertz. Okay, so you end up with 1 times 10 to the 8 hertz. All right, so let's look at a couple more together real quick. So if you feel ready, pause the video and try this next one on your own, and then we'll look at it together. So it says the radio waves of a particular AM radio station vibrate 680,000 times per second. So this is our hertz, or our per second, which is our frequency. So that's my nu. What is the wavelength of this wave? So we're looking for wavelength. So again, they're not going to reference C at all. That's just something you have to know is the constant. So C is lambda times nu. I'm looking for lambda or wavelength, so how do I get nu on the other side? Well, remember, do the opposite. Right now we're multiplying. The opposite of multiplying is dividing. So I divide it to the other side. So lambda is C divided by nu. Once I know that, I can just plug in. So C is 3.0 times 10 to the 8 meters per second. And my nu is 680,000. Ooh, sorry, that zero got kind of weird. Times per second, or hertz, or what I'll write is 1 per second. So if you look, those seconds cancel and I'm left with a unit of meters, and once I divide this, I got 441.2 meters. Alright, so hopefully if you tried that one on your own, you got it right. If you didn't, try the next one, but I will say be careful of the centimeters, you're going to have to change that. Alright, so pause it, try it if you feel ready, and then we'll look at it together. So a global positioning satellite transmits a radio wave with a wavelength of 19 centimeters. So there's my wavelength. What is the frequency of the radio wave? Now you may wonder, why don't they ever have me solve for C? Well, C is a constant, so no one's going to ask you to solve for C. So just be prepared to always rearrange this formula. Alright, but the problem is, what did I tell you wavelength has to be in? Well, our speed is in meters per second. So our wavelength has to be in meters. Okay, so let's look at how to convert that. Alright, we have 19 centimeters. There are 100 centimeters in a meter. So 100 centimeters in 1 meter. And so once I divide, I get 0.19 meters. Or if you know how to move your decimal using King Henry Dides, you're more than welcome to do that too. However, this is a much better way of converting, especially if you're trying to get to chemistry, because moving the decimal doesn't work in that class. Alright, so we get 0.19 meters for our wavelength, and so then we get our formula rearranged. So C equals lambda nu, we're solving for nu, so how do I get lambda on the other side? We'll do the opposite. Right now we're multiplying, so I'm going to divide both sides by lambda. So nu is C over lambda, and now just plug in. So my C is 3.0 times 10 to the 8 meters per second. And my lambda, we decided, was 0.19 meters. And so if you look, those meters cancel. See, a centimeter and a meter won't cancel. That's why we had to change it. So once I divided, I got 1.6 times 10 to the 9. And then again, we're not left with seconds. We're left with 1 over a second, which is a hertz. Or you're more than welcome to write 1 over second. But you cannot just write seconds as your units. That is not correct. Alright, so hopefully you got one or both of those right. And so let's move on. So electromagnetic radiation behaves sometimes like a wave and sometimes like a particle. Evidence for a wave includes the fact that light can produce constructive and destructive interference. So this is a picture that I kind of found online. I thought it was kind of neat. It says light is a, because there's this whole argument. Is it a wave? Is it a particle? And so if you look at it real closely, you can see it is a wave, or you can see it is a particle. I don't know which one you saw first. I always see particle first when I look at that before I see wave. And so one of the pieces of evidence that it is a wave is that it does constructive and destructive interference when the waves overlap, which we've talked about that in previous videos. Evidence for a particle includes the fact that light causes the photoelectric effect. What is the photoelectric effect? Well, it's the emission of electrons from a metal caused by light striking the metal, and it's called photoelectric effect. So here's a metal. And what happens is when certain frequencies of light shine on it, they can emit electrons. And that should only happen if light is actually a particle. Now what is it in reality? It's a photon. That's the light particle that we call it. We think of it as like a little bundle of energy that travels in a wave pattern. So it's kind of both. We say light has a dual wave particle nature. In 1905, Albert Einstein proposed that light and all electromagnetic radiation consists of packets of energy called photons. Each photon's energy is proportional to the frequency of the light. So in other words, the higher the frequency, the higher the energy of the photon. Photons travel outward from a light source in all directions. The intensity of light decreases as photons travel farther from the source. So think about this. If somebody's standing this close to you and shines a flashlight in your eye, that is going to be very intense. However, if someone stands all the way down the hallway of the school and shines a flashlight in my eye, it's not going to be as big of a deal because I'm further away from the source. And so as those photons spread out, they become less intense to look at. So think about a flashlight. When you look, it kind of spreads out like this. And so as it gets further out, those photons are more spread out, so it's less intense. So, section assessment. How fast does light travel in a vacuum? Well, that is your value of C. 3 times 10 to the 8 meters per second. 3 times 10 to the 8 meters per second. So number 2, what makes electromagnetic waves different from one another? Well, they're traveling at the same speed, so what's different is their wavelength and frequency. Their wavelength and frequency is different. So number 3, what happens to the intensity of light as photons move away from a light source? Remember, as those photons spread out and we get further away from the light source, the intensity decreases. The intensity decreases. All right, and here's another math problem. So maybe pause the video, try this one. I will tell you, be careful. This is kilohertz, okay? Kilo means 1,000. All right, this is kilohertz, so you'll have to change that. Otherwise, don't pause the video and just let me do it with you. But if you feel confident in changing it, pause the video and try it. So it says, what is the wavelength? So I'm looking for wavelength of an AM radio wave in a vacuum if its frequency, there's my nu, is 810 kilohertz. All right, well first we got to deal with this kilohertz. Kilohertz is just like kilometer, just like kilogram. 1,000 hertz equals a kilohertz. So I take my 810 kilohertz and I say, okay, well 1 kilohertz is 1,000 hertz. And so once I multiply, I would get, oh, I'm running out of room, 810,000 hertz. Okay, because we can't plug in a kilohertz because there's nothing for me to cancel out with that. All right, so let's rearrange our formula. So C equals lambda nu. I am solving for wavelength, which is lambda. So how do I get nu on the other side? Well, as always, if you're multiplying, you divide it to get it on the other side. So I divide both sides by nu. So lambda is C divided by nu, and then I just plug in. So C is 3.0 times 10 to the 8 meters per second. We decided our frequency is this. Remember, we had to change it from kilohertz to hertz. So it's 810,000. And remember, I always change hertz to 1 over a second when I plug it in so I can see what's happening with my units. So those seconds cancel. I'm left with meters. And so once I solve, I got 374.5, and my unit is meters. All right, so the C equals lambda nu formula is really the same as the speed equals lambda nu. It's just in this case, we know the speed of all electromagnetic radiation is the same as the speed of light, which is 3.0 times 10 to the 8 meters per second. So hopefully you understand a little bit more about electromagnetic waves and how to calculate frequency and wavelength.